Welcome to this presentation about the efficient control of conditioned air from air handling units. As you will see, this is quite an issue. We described extensively in another lecture that even with an all-air system, it may be useful to apply temperature readjustment at room level, adding a bit of cooling or heating in the room, depending on the specific needs of the room. A room with more occupants and oriented to the sun is more likely to need cooling, while a room with only one person and seeing no sun will need heating. This raises the question at which temperature the conditioned air coming from the air handling unit should be provided to the rooms. Let's start with an all-air system and review how it works. In an all-air system, the complete heating demand and the complete cooling demand of the rooms must be delivered by the air handling unit. You learned how to calculate the heating and cooling demand in another course by making the balance of all transmission and infiltration heat flows and the solar gains and internal heat gains. In this balance, we assume that the indoor air is at temperature Ti. If the conditioned air is to bring all needed heat or cold, its temperature must be warmer than the room air in heating mode and cooler in cooling mode. Otherwise, no heat can be delivered or removed. You remember that there is always a temperature difference needed to exchange heat. Let's look at heating situation. The hot air from the AHU at TAC comes into the room where it is cooled down, giving its heat to the room air, just like a heat exchanger would do. In reality, it is a bit more complicated than that because there is no heat exchanger, but a mixing process with room air, the temperature of which increases or decreases continuously depending on the room energy balance. Therefore, it's a dynamic process and it goes much too far to describe it in this course. However, it works very well to just consider the room to have a constant temperature Ti and the air from the AHU to be a perfect heat exchanger delivering return air at Ti. So let's do that. The quantity of heat exchanged is the quantity of heat delivered by the AHU, which is ρ times volume flow rate of air from AHU times Cp air times Ti minus TAC and is equal to Q demand. And the AHU delivers the heat needed to bring the outdoor air from T0 to TAC. In cooling mode, we would have exactly the same, only TAC would now be lower than Ti and Q demand would be negative because cooling is removing heat. But as you know, we just use the absolute value. Anyhow, you can play with two variables, the volume flow rate VA and the temperature of the conditioned air TAC to bring the needed energy in the room. The larger the volume flow rate, the closer TAC will be to Ti and conversely. You see on this graphic the relationship between the temperature difference TAC minus Ti in green and the corresponding volume flow rates in blue, delivering the energy demand in purple. Either you choose for a small volume flow rate with the advantage of having small ducts, but then you need a high temperature difference. In heating modes, that could mean that TAC would be over 35 degrees and in cooling mode below 12 degrees, which feels very uncomfortable as you learned in a course on local discomfort. Conversely, choosing a high volume flow rate has the disadvantage that very large ducts are needed, but the advantage that TAC will be much closer to the room temperature and therefore that will be much more comfortable. So the final choice will depend on the client and architect preferences. Let's look at the temperature control first. AHUs controlled only by temperature are called CAV systems. CAV is the abbreviation for constant air volume flow rate. In a CAV system, the volume flow rate of air is kept constant whatever happens. If the AHU operates one room, it is easy. You can control the indoor air temperature Ti with a room thermostat, for instance. The set value is TSI and a measured value TTI. Depending on the set value, the actuators, which are the heaters and coolers in the AHU, are switched on or off. As a result of this, TAC, the temperature of the conditioned air supplied to the room, varies. Well, if there was only one room, that would work perfectly. But an air handling unit operates, in general, many rooms at the same time. The heat and cold demands in these rooms, as well as their temperature, will differ depending on their location and occupancy. On which room thermostat will the control be done? We can choose one room, but then all others will be too warm or too cold, most probably. The solution there is A. To design correctly zones, meaning that in an HVAC zone it is important that all rooms have a quite similar behavior, and B. To average on all rooms. Therefore, the control parameter is not the indoor air in the room, but the average temperature of the return air, which is measured in the main duct coming back to the air handling unit. So it is not measured in the room branches, but in the main duct. The set value is in general obtained from experience and tryouts in the specific zone, which the S value results in lower comfort complaints. You understand that all in all, such an all-air system cannot ensure comfort in all rooms. Which is a reason to use systems with readjustments at room level. The conditioned air needs to deliver a smaller part of the energy. The other one is provided at room level. So, if the supplied temperature is too cold, hydronic heat comes in, and if the supplied temperature is too warm, the hydronic cold comes in. This can be controlled manually or by a room thermostat. In principle, the hydronic readjustment has limited power. It is a readjustment system, not meant at providing a lot of it or cold. So if TAC is not right, it may still be too cold or too warm in the room. That's why there is still a central control on the return temperature, just as we had before. What happens now when there are many rooms? Well, the same as before, there is a central control on the average return temperature in the main duct. Here too, it is important to design a zone with rooms of similar demand, but this time that is more in terms of energy than in terms of comfort. The comfort will be quite okay because of the room's hydronic systems, while energy may be wasted. It also happens quite often that the hydronic cold and heat generation systems are not placed in the room, but are common to several rooms being placed in the duct leading to these rooms. They are zone systems, therefore. In a variable air volume system, VAV, the temperature TAC is kept constant all time and the volume flow rate VA is controlled. Depending on the measured value in the return duct, the volume flow rate VA is changed by adapting the rotational velocity of the fan. And of course, to keep TAC constant, we need to control it as well, like that by controlling the heater and coolers. Please note that there is here no link with the indoor air temperature. This VAV system has two big advantages over the CAV one. First, at partial load, the volume flow rates are strongly reduced, by which the velocities in the pipes are reduced as well, leading to much less pressure loss and therefore much less fan energy. Because most operational hours are in partial load, this makes these systems very energy efficient. Note that the controlled volume flow rate VA must always be kept above the minimal value needed for hygienic air. Second, as the temperature TAC is kept constant, uncomfortable very high or low supply temperatures are avoided, by which the comfort increases, especially if there is readjustment at room level, like in this slide. If it is a VAV system without room readjustment, very high flow rates may be needed, which would create very high air velocities at room level, which would be uncomfortable. So, in a VAV system, TAC is constant. But how constant? This raises the problem how to choose TAC. Here too, it may be somehow based on trial and error during operation, but some guidelines can be used. First, you could apply one constant temperature all over the year, for instance 22 degrees. This could work in a climate with moderate and constant outdoor temperature all over the year, but in many other climates it will result in too high room temperatures in summer and too low room temperatures in winter. So let's look at the second solution, in which TAC varies with the season. It is constant, but it varies. It is a VAV system, but only during a season. In the very cold season, a high temperature is applied and TAC is decreased linearly with the outdoor temperature. The set value is decreased. At moderate temperature, the set value of TAC is kept constant, and at high temperatures it is decreased. Main disadvantage here is that at peak load it may be uncomfortable to have such high temperatures in winter and such low temperatures in summer. So finally, it is a bit of tuning. Depending on the climate and temperature profiles, it can look like here. For instance, the blue line in the middle, with TAC around 16 degrees Celsius, is quite typical in reasonably insulated Dutch buildings. In poorly insulated buildings or in colder climates, a profile like the orange one would be preferred, while in passive buildings and in hotter climates, TAC will be decreased with a lot of attention to staying within a bandwidth, ensuring comfort. So in the end, also in a VAV comfort, there is some kind of TAC control. By the way, modern systems would adapt the set value of TAC according to the measured outdoor temperature TO. In even more modern systems, it could be adapted based on temperature predictions, what is called Model Predictive Control, MPC. Finally, let's look at the effect of the temperature of the conditioned air TAC on the flow patterns in the room. As you can see here, the pattern depends a lot on the position of the air inlet valve in the room. This is just to give you an idea. The actual flow patterns depend very much on the valve design and the velocity of the air jet when leaving the valve. The position of the exhaust valve does not change very much the patterns and is not shown in the figure. When TAC is smaller than the room temperature, in cooling mode, therefore, placing the supply valve on the top of the wall or below, blowing up, will create a good circulation and mixing of air. If it is supplied below horizontally, the air will remain below, and it may be that the room is not entirely ventilated. If we look now at isotherm ventilation, no heating or cooling, therefore, the mixing is right in all cases. In heating mode, it is the reverse as in cooling mode. Warm air goes up, cold air down, and blowing the air from below will be more efficient than blowing it horizontally from above. In what is called displacement ventilation, the velocity of air is much smaller and the air is supplied with a large number of small valves. On the other side of the room, a large number of small valves is used to exhaust the air. This time, you can see that there are no swirls. The air moves straight away. The whole room is ventilated, but there is almost no air mixing. Typically, this will be used in rooms where spread of pollutants should be avoided, like clean rooms, operation rooms in hospitals, theaters in which the valves are placed in the chair itself. The direction of the flow depends on which way one wants to transport the pollutants and also on the expectation of the systems being used essentially for cooling, that will be then from down under, or essentially for heating from below to above, or just for ventilation. We have come to the end of this lecture, in which you have learned about energy-efficient control of conditioned air supplied by air handling units. It can be controlled either by controlling the flow rate or the temperature. We explained the control issues in zones with multiple rooms using the traditional CAV system, which is not very efficient, neither comfortable. We then switched to the VAV system, variable air volume, which avoids high pressure loss and decreases therefore fan energy while ensuring more comfort. We looked at suitable air condition temperatures and at their effect on the airflow patterns at room level. I hope you enjoyed this lecture. Thank you for your attention.